Chapter 1 left us with a target and a difficulty. The target is the overpotential. The extra voltage a real anode demands beyond the 1.23-volt thermodynamic price. The difficulty is that computing it appears to require simulating an electrified interface. A charged surface, a liquid electrolyte, solvated protons swimming about, and an electrode potential that is not a natural quantity in a quantum chemistry code at all. This chapter presents the idea that made computational screening practical anyway. By the end, you will take 4 numbers describing how a surface binds its intermediates and read an overpotential straight off a diagram. Oxygen evolution on a surface does not happen in one concerted event. It proceeds through proton-coupled electron transfers, each removing 1 proton and 1 electron and leaving a different oxygen-containing species bound to the active site. Write an asterisk for a clean site. Step 1. The site plus water gives star OH, a proton and an electron. Step 2. Star OH gives star O. Step 3. Star O plus, a second water gives star OOH. Step 4. Star OOH releases oxygen and regenerates the clean site. Add the 4 together, and the intermediates cancel, leaving exactly the half reaction from Chapter 1. 3 observations before we start computing. First, Step 3 is where the oxygen-oxygen bond forms. Steps 1 and 2 progressively strip hydrogen from an adsorbed water molecule. Step 3 brings a second water in and joins its oxygen to the one already there. That is the chemically hardest thing this reaction has to do. Second, every step transfers exactly 1 proton and 1 electron, and because the counts are identical, an applied potential acts on all 4 steps in the same way. Third, the site returns to where it started. A catalyst is, by definition, something that comes back. To compute the free energy of Step 2, you need the products minus the reactants. The surface terms are ordinary electronic structure calculations, hard work, but standard work. The trouble is the other 2 terms. The chemical potential of a proton in solution means simulating a solvated proton in liquid water, with the hydrogen bond network reorganizing around it, averaged over configurations. That is a research project whose error bars would swamp the differences we care about. The chemical potential of an electron depends on the applied potential, which a standard periodic calculation has no way to set. Both appear in every step, always together. That last observation is the whole idea. We never need the 2 chemical potentials separately, only their sum, and the sum has a reference system where it is trivially known. By definition of the reversible hydrogen electrode scale, at 0 volts, a proton plus an electron is in equilibrium with half a hydrogen molecule in the gas phase, so their chemical potentials are equal. The awkward pair is replaced by half of a gas phase molecule. Then the potential. Each step releases 1 electron, so raising the electrode potential lowers every step's free energy by E times U compute once at 0 volts. The rest is arithmetic. The 4 numbers we feed the code are free energies, not raw electronic energies, and the difference matters. Each step's value is assembled from 3 contributions. Density functional theory electronic energies of the surface, with and without each adsorbate, and of the gas phase references. 0-point energy corrections, because bound oxygen-hydrogen and oxygen-oxygen vibrations carry substantial 0-point energy that differs between the 3 intermediates, so it does not cancel. And entropy terms, since adsorbed species have far less entropy than the gas phase molecules they came from. We quote no values for these. Inventing representative numbers would be false precision. Now the constraint. The 4 steps sum to the overall half reaction, whose free energy is fixed by thermodynamics and reads, per electron, as 1.23 electron volts. So for any catalyst whatsoever, the 4-step free energies at 0 volts sum to 4.92 electron volts. Read that carefully. The catalyst controls how the 4.92 is divided among the 4 steps. It does not control the total. A surface cannot make oxygen evolution cheaper. It can only make the 4 installments more evenly sized. Design is a redistribution problem, not a reduction problem. Here is a fictitious surface we call catalyst A, whose 4-step energies are illustrative teaching values, not measurements and not attributable to any real material. At 0 volts, everything is uphill and the climb ends at exactly 4.92 electron volts, as the sum rule requires. At 1.23 volts, the endpoints balance. It starts at 0 and ends at 0. Yet the path between them is not flat. Step 2 is still positive by 0.37 electron volts. The reaction is blocked not because the overall thermodynamics forbids it, but because one step still does. For the cycle to run downhill everywhere, every step must be non-positive after the shift, so the applied potential must be at least the largest step. The largest single step, therefore, sets the potential you must apply, and the step it belongs to is the potential limiting step. For our illustrative catalyst A, the largest step is 1.60 electron volts, at step 2. At 1.60 volts, that step flattens to exactly 0, and every other step is negative. The theoretical overpotential is the excess over the thermodynamic price. 1.60 minus 1.23, or 0.37 volts. The calculator takes 4 step energies, checks the sum rule, shifts every step by the applied potential, and reports the overpotential and the limiting step. All 3 catalysts here are fictitious, and their numbers are illustrative teaching values. Each sums to 4.92 electron volts, as it must. Their overpotentials span 0.05, 0.37, and 0.52 volts on the same fixed total. Catalyst B still pays the most, because one step costs 1.75 electron volts, and a catalyst is only as good as its worst step and still pays the most, because one step is 1.75. A catalyst is only as good as its worst step. Let us recap. Oxygen evolution proceeds through 4 proton-coupled electron transfers via star OH, star O, and star OOH, and they add up exactly to the half reaction. The computational hydrogen electrode replaces the solvated proton and the electron with half of a gas phase hydrogen molecule, and the applied potential then enters as pure arithmetic. The sum rule fixes the total at 4.92 electron volts for any catalyst. The largest step is potential limiting, and our illustrative catalyst A gives 0.37 volts. If 4 equal steps are ideal, why has nobody built one? Next, scaling relations and the volcano.